employee of Sud Chemie, it's my honor this morning to introduce our keynote speaker for this session, Leo Manzer. He's the winner of the 2001 Hydrodynamic Award. He has received numerous awards, patents, publications over the years, and he's employed by DuPont Chemical Company, and his efforts there led to the discovery and development of new catalysts for the synthesis of alternatives to fluorocarbons. He's a fellow of DuPont Central Science and Engineering Laboratories in Wilmington, and as a DuPont fellow, he has achieved one of the company's highest levels of personal and professional recognition for scientists. He's been involved in all aspects of catalysis at DuPont and has led the effort for R&D, like I said before, in the chlorofluorocarbons. His interests cover a wide range of catalytic technologies in the areas of homogeneous and heterogeneous catalysis, involving hydrocyanations, oxidations, hydrogenations, acid-base, and fluorocarbon catalysis. He's also initiated and led a major effort in the converting of natural gas to liquids for Conoco, and he's discovered new catalysts for the Fischer-Tropsch reaction. Dr. Manzer has recently taken the initiative to find new opportunities for catalysis in life sciences and biomaterials, and has already found new processes that combine both the bio and chemical catalysis. So if you'll join me in welcoming Leo this morning.
Thank you, Bill. It's a pleasure to be here, and I want to thank the organizing committee for the opportunity to visit the Tri-State Catalysis Society. Vadim asked me to come here, and I thought, great, I've never been to Cincinnati, and I guess I still have to wait to visit Cincinnati maybe next time around. But I did want to come and talk to you today about an important aspect. I'm not an expert at all in global warming or those kind of climate type issues, but I think it is an opportunity for us in the catalysis community to speak out a little bit and say that catalysis is important to all of us and can have a small but an impact on global warming. My involvement here started with a call from Alex Bell back in 1999. He and Tobin Marks were organizing a workshop on carbon dioxide, all aspects of carbon dioxide in Santa Fe just about 2 years ago, Alex. And that was a really neat workshop. We dealt with all kinds of issues. And then he called me up again. Every time my telephone rings and it's Alex, I know I'm in for some work ahead of me here. But he called me up last December and organized another workshop in Washington, sponsored by the National Research Council, on carbon dioxide and issues related to carbon dioxide. And that was actually a really fascinating workshop dealing with solar panels and wind and alternate energy and all kinds of neat things at the workshop. I learned an awful lot there. So this has been an important issue. I think it's an opportunity for us to promote catalysis. There are two big reports coming out of both of these workshops, and I guess they are going to issue here very shortly. So if you're interested, go ahead and look at those reports, and you can see a lot of really neat things. So let me just comment today then on some of the key conclusions from the workshops. Clearly we have to become more efficient. We waste an awful lot of energy. Increasing our efficiency would be a step in the right direction. We've got to reduce our dependence on carbon-based fuels, go to hydrogen economy, things of that sort. There's a fairly significant effort on sequestering carbon dioxide out of the atmosphere. Sounds like an awfully difficult job when you're looking at parts per million, but there are ways that people are thinking about to actually trap the CO2 out of the atmosphere to get it down. The reports comment on some key research opportunities to move over to a hydrogen economy, learn how to activate, utilize hydrocarbons, and that's a very, very, very neat catalytic opportunity for us. Use carbon dioxide, convert it to other chemicals, develop more efficient transportation systems, and then there's a general statement in the report to go after and develop new emerging technologies. It's hard to know where they're going to go, but there is an opportunity, lots of opportunities for new technologies. So those are some of the issues, conclusions in the reports that we'll issue. The problem is really pretty enormous when you look at it. The amount of carbon dioxide, this was a study done by an intergovernment panel on climate change back in 1992. And back in 1990, as a base point here, there were 6 billion tons of CO2 emitted to the atmosphere every year. And that number, if you look at the end here, by 2095, going up to 20 billion tons of carbon dioxide, which may or may not have an effect on the climate, but I think most of us will agree that's probably not a trend that you want to continue, and it most likely will have a significant effect on warming the atmosphere, oceans rising, polar caps melting, and so on and so forth. So that's the projected growth in CO2 emissions. Then there were a number of studies projected at how do you keep the level constant or bring it down to 550 parts per million, which is 2x the pre-industrial revolution levels in the atmosphere. So this is where the policymakers would like us, and the environmentalists would like us to get to. So the difference here is, almost 20 billion tons a year of CO2. So that's our challenge in a small way, is how do we help to reduce this amount of CO2 to the atmosphere? Well, if you think about catalysis, one of the areas obviously is oxidation catalysis. We do make, in many of our processes, carbon dioxide through a non-selective oxidation of a hydrocarbon. Instead of making the oxidized products that we're interested in, we make CO2. It's not a large amount, but hey, every little bit helps, and that's the issue that we're trying to promote in the area of oxidation catalysis. So that's what I'd like to talk about today. I'm not going to tell you anything you probably don't already know, but I'm going to cover a lot of different areas of oxidation catalysis, comment on the current trends, some specific areas of oxidation catalysis, oxidations under anaerobic conditions, kind of state-of-the-art in alkane and aromatic oxidations, the use of materials other than oxygen or air, such as N2O, hydrogen peroxide, hydrogen-oxygen mixtures, and even CO2 as an oxidant is a technology that's developing. There are some new ways to make the products we're interested in that don't involve oxidations. I'd like to give you some ideas in that area, and then finally some comments. Most of you have probably not seen a catalytic oxidation reactor. These are very large systems. Here is a typical reactor for the oxidation of orthoxylene to phthalic anhydride. This particular reactor is 25 feet in diameter, 9 feet, not a very tall reactor. Some of these reactors get to be huge, containing 20, 30,000 tubes, 20 feet long, all packed with quarter-inch pellets, and each one of those tubes has to be packed individually. These are incredibly expensive, time-consuming operations, and high investment required to carry out these oxidation processes. And the reason for that is because organics and air form flammable mixtures. So in order to prevent the reactors from blowing up, you have to stay below the flammable limits. And that oftentimes means you're operating at 1 or 2% hydrocarbon in a stream. So here you've got one of these big reactors I just showed you. You're passing 1% hydrocarbon and 99% air through that reactor. And all of the equipment downstream, the distillation columns and everything, has to be sized to handle all of that air that's in there, when you really only want to deal with a small amount of organics. So that's why it's a high investment process, because of the flammability issues. So you see the investment is sized because of all that air. They're incredibly exothermic, so you get a lot of heat exchange investment to take the heat from the reaction, prevent the reactors from running away. Extensive refining, which is another global warming issue because it takes energy to refine and boil up and distill all of this inert material that goes through the process. And the selectivities are generally low. So you've got to distill and take this small amount of product and purify it. So if you're feeding, for example, 1%, take for example butane to maleic anhydride. If you have a 50% selectivity, you've got a 0.5% maleic anhydride that you take out of a stream containing 99.5% other stuff. So it takes a lot of refining and uses a lot of energy to do that. Some of the selectivities of commercial oxidation processes are shown here. They're not very selective generally. This is one of the least selective of all catalytic processes. And take, for example, the bottom reaction here, the oxidation of butane to maleic anhydride. Operated on a very large scale commercially, 60% selectivity on the average. Well, a plant that makes 200 million pounds a year of maleic anhydride actually makes 500 million pounds a year of carbon dioxide. So you're really running a carbon dioxide plant with maleic anhydride as a byproduct in this process. But that's typical of what happens in many of these oxidation processes where you make carbon dioxide. So you can see there 500 million pounds a year out of a single maleic anhydride plant. So if you could find a way to increase the selectivity, you can reduce the CO2 emissions. So the first thing I want to deal with is anaerobic oxidations. Alex mentioned yesterday the Mars-Van Crevelen mechanism. And the idea there, I'll just repeat what he said yesterday, is to take the lattice oxygen of a catalyst, react it with a hydrocarbon such as butane to make maleic anhydride. The oxygen that comes out causes the catalyst to be reduced. That reduced catalyst then is moved to a separate zone, reacted with air or oxygen to regenerate the more oxidized species, which then goes back over into the other reactor and goes round and round and round the loop. So you're using the lattice oxygen as a source of the oxygen to make the maleic anhydride. And the advantage there, of course, is you're eliminating a lot of radical reactions because the gas phase oxygen or air is separate from the hydrocarbon. The other advantage is that you are you can avoid any flammable limits because you're keeping the air separate from the hydrocarbons. So you can run these reactions 40, 50, 60% hydrocarbons. So you've got much higher concentrations of the products that you're interested in downstream. Now there's some really important requirements that need to be met. Because this is a stoichiometric reagent, all of the oxygen is coming from the lattice. So you've got to be able to pull a fair amount of oxygen out of that lattice on a single pass. Otherwise, it's going to cost you an awful lot of money to circulate the stoichiometric reagent around and around. So you've got to have a lot of oxygen available to oxidize the hydrocarbon. You also need to run this regeneration step at about the same temperature as the reaction takes place. Otherwise, you're heating or cooling millions of pounds of solid on every cycle, which you can't afford to do either. So there are a lot of issues that need to be addressed. The catalyst is the most important, most costly part of this overall process. If the catalyst is not attrition resistant, if it falls apart, it doesn't stand up to millions of cycles, then the process is also uneconomical because these catalysts are not cheap by the time you get them from companies like Sudchemie and Degussa and others. So you've got to make sure the catalyst stays in there for a very, very long time. Now let me give you some examples where this has been looked at over the years. The first example was probably the M-oxidation of propylene to acrylonitrile, but I haven't got any data on that reaction. I've asked the folks at BP and Soheil, and I can't get any data there. So I'm going to show you the first example that I've been able to come up with. It was a process operated by Lummus in 1973. Actually went through the pilot plant stage. They're looking at the M-oxidation of orthoxylene to the dinitrile, the aromatic orthodinitrile here. And they run this in this anaerobic environment. In the reactor, they're feeding the aromatic orthoxylene and ammonia. There's no oxygen present. The catalyst provides the source of the oxygen, the M-oxidation. So they do the M-oxidation in this reactor to make the dinitriles. Dinitriles come out the top. The reduced catalyst is then separated, goes off into a small reactor where the adsorbed dinitriles are stripped off, oftentimes with steam or something like that, and they go back into the reactor and are separated. The reduced catalyst then goes through the regenerator where it's reacted with air or oxygen, regenerated, comes back over here and goes around and around and around the loop. This is a pretty nice process. They commented that it was much safer because you're separating the oxygen from the orthoxylene. The non-selective radical reactions were eliminated, so they reported very high yields, and they also said the investment was significantly lower. Now, I don't know why this did not go commercial, but it was a wonderful example of one of the first examples of anaerobic oxidations. I think the second biggest effort was done in the early to mid-1970s by Arco Chemical, John Sofranco and his group. They were looking at methane oxidative coupling to ethylene using a metal oxide catalyst. The composition here, a manganese-magnesium catalyst on silica with some promoters in there. This is an amazing reaction. It was run in a cyclic mode. The temperature was around 850 to 900 degrees centigrade. So they were cycling catalyst around the loop at nearly 900 degrees centigrade. And you can see two modes of operation. One is the cyclic mode, which is the anaerobic mode I've been talking about. They were able to get 22% conversion of the methane. And the selectivity to ethylene around 61%, and COX was 22%. If they ran it in a co-feed mode where they're feeding air along with the methane in a fixed bed or fluid bed or cyclic operation, they made much more CO2, so 22 to 34%. So once again, nice example of an oxidative dimerization reaction in an anaerobic mode. At the time, I think they were saying they needed oil at $30 a barrel, so maybe it's time to go back and relook at this technology again. But beautiful example of a technical success, but an economic failure. Happens to us all the time in industry. Another really neat example by Monsanto. They were looking at making styrene starting with toluene. Used a potassium-promoted bismuth oxide catalyst. This oxide catalyst was used as an oxidant to oxidatively dimerize the toluene to the trans-stilbene. Then the second step of their process was an acid-catalyzed reaction. So they fed the trans-stilbene with ethylene, picked up half of the ethylene, put it on the end here as this broke in half to make styrene. Really slick chemistry. The catalytic air process, the results are shown here, 38% conversion, 72% selectivity to the trans-stilbene. When they ran it in the anaerobic, the stoichiometric mode with the metal oxide, you can see here that the selectivity was 9 or so percent higher by keeping the oxygen out of that process. This overall reaction is a very nice way to make styrene, uses half of the conventional amount of ethylene, and looked very good. Once again, another technical success, but I guess the situation at Monsanto at the time didn't allow them to go forward. But it was scaled up through the pilot plant stage and worked very well. Another example that went through the pilot plant stage was operated by Dow Chemical. They were interested once again in making styrene by taking propane, reacting it with a magnesium modified molybdate catalyst to do an oxidative dehydrogenation with the oxygen coming once again from the lattice of the catalyst here to make butadiene, which they then dimerized to give the vinyl cyclohexene, which then dehydrogenated to styrene. Looked like a great way to go, starting with butane to make styrene. They ran this process not in a real continuous mode, but they ran it in a fairly large scale reactor, pulsing in butane and pulsing in oxygen. So kind of doing it alternately between anaerobic and the regeneration mode. The data is shown here, and talking to Craig Murchison, who did a lot of this work, they did see a significant improvement over the straight dehydrogenation of butane to butadiene. So once again, great technical success, went through the pilot plant stage and failed because of economics. I think probably one of the most striking examples I could find was this report by Amig of Germany, who was looking at the oxidative dimerization of isobutylene to this dimethylhexadiene, which goes into certain specialty chemical applications. In the aerobic mode, where you're feeding air to do the dimerization, conversion 24%, selectivity was very low at 38%, coming up with a 9% yield in this process. Now, by leaving the air out of the reaction, doing it strictly in an anaerobic mode with the catalyst that he was using, look at the big difference. The conversion drops in half, but the selectivity goes from 38 to 90%. Huge difference in selectivity, coming out with actually an overall yield in the process that's higher. Conversion is low, but the big difference in selectivity makes up for it. So this is a wonderful example, once again, of showing what happens if you take the oxygen out of the process. You can reduce CO2 emissions very significantly. Recently, Oakham and DuPont, we had a joint development effort with them on a patent issued, your world patent, on the oxidation of propylene to acrolein and acrylic acid Very complicated bismuth molybdate catalyst. I guess the numbers to look at are shown in this column here. The selectivity in this, it was run in a riser reactor. In this case, it was propylene, steam, and nitrogen, no oxygen in the process. You can see the very high levels, up to 20% propylene fed to that reactor with 96 to 100% selectivity to the combined acrylic acid. Wonderful results. The only results that I can report on in the patent are shown down here at about the same conditions. 350 degrees, 21% propylene in the feed, 95% selectivity. Now they dropped the propylene a little bit, well they dropped a lot, down to 10%, put 7% oxygen in, and the selectivity dropped to 82%. So once again you can see a reasonable decrease in selectivity when gas phase oxygen is present over these metal oxide catalysts at high temperatures. Okay, the only commercial example that I know of is our process that we've worked on for a very, very long time, went commercial in 1996, involves the oxidation of butane to maleic anhydride as an intermediate. Most people purify, separate the maleic anhydride, and reduce it down to tetrahydrofuran. We actually come out of our reactor with a water quench it as aqueous maleic acid. The maleic acid is then hydrogenated directly out of that aqueous solution in a slurry bubble column reactor to make tetrahydrofuran. So this example, I'll show you some more details in a minute here. We feed as high as 50% butane in that process. There's a novel vanadium pyrophosphate catalyst I'll tell you a little bit about. We do the water quench and then eventually make tetrahydrofuran, which goes into spandex and lycra fibers, some of those wonderful fibers that we sell. So here's the schematic of the circulating fluid bed reactor. Butane is fed in the bottom along with the vanadium pyrophosphate catalyst. Comes up through the riser. The VPO catalyst reacts with butane to make maleic anhydride that's separated. The reduced catalyst, it comes out of the reactor into a cyclone. The cyclone then sends the reduced catalyst to a separate fluid bed reactor where it's reacted with air to regenerate the oxidized catalyst, which goes around the loop. So you can see this is the nature of what's happening in the stoichiometric anaerobic oxidation. It's the most critical feature. Requires that the catalyst stay in there for a very, very long time. And that was a big job for us initially. These VPO catalysts are soft, not very strong. As soon as you put them into a moving bed reactor, particularly a riser that's chock full of heat exchangers, so you can take the oxygen or take all the heat out of that riser reactor. So attrition resistance was really important to us. And one of our silica experts, Horatio Bergna, found that he could take sodium silicate and ion exchange it. And this required, he had been with us for like 50 years, 50 years of experience to learn how to do this, to stabilize silicic acid, monomeric silicic acid. It wants to dimerize and trimerize and eventually give you silica very easily. If you don't treat it right, you'll end up with silica again. So stabilizing this silicic acid was critical. Then he took that aqueous solution of silicic acid, put it into a spray dryer, and along with granulated, micronized, powdered VPO catalyst. And in that spray dryer, the water moved to the surface, carried the silicic acid with it to the surface, dried, and created a very strong, very porous silica coating on the surface of the catalyst. So you ended up now with a catalyst pellet, the right size for a fluid bed or a transport bed reactor. The silica was on the surface, very porous. Butane, maleic could go through it very, very nicely, but did not affect the selectivity at all. This shows an electron micrograph of the nice, beautiful, round VPO particles coming out of the spray dryer, just set up just beautifully for fluid bed operation. There is this very porous silica shell on the surface, and that encapsulates like a tennis ball, with the outside surface being the silica and the inside being chock full of VPO, porous VPO, very soft catalyst. So the butane diffuses through that outer shell, reacts, and the maleic anhydride comes back out again. This picture's been around for a long time. Well, I guess I took it out. But you can, in fact, leach this out, and you can see a very nice hollow shell of the silica. There's only 8% there. Doesn't have an adverse effect on the performance of the catalyst at all. So the catalyst attrition has worked out extremely well, and this is a little bit of data that I can show that shows the advantage of running with no oxygen present. This is actually a small little reactor we ran in the laboratory, but if you run with as much as 50% butane, you can maintain selectivities well over 60% versus the more traditional 50 to 60% that you see in fixed bed reactors or even fluid bed reactors with only 1% or 2% butane in the feed. So there is an advantage from a selectivity standpoint and an investment standpoint in running the butane oxidation process that way. One of the biggest issues we faced very early on in this process was to understand the hydrodynamics in this riser reactor. We've got all these heat exchangers in there. Was the catalyst going to be attrition resistant? What kind of performance were we going to get? So we actually built this full-scale riser reactor at Ponca City, Oklahoma, our Conoco facility at the time when we owned them. And we used this riser. It was about a foot and a half to 2 feet in diameter. And it operated for a period of time, and it demonstrated that this process would work as expected. We then commercialized the process in Asturias, Spain in September of 1996. And you can see this is a layout of the plant, a photograph of the plant, not a very good one. But here's the riser reactor to take the butane to the maleic anhydride, which is quenched as the acid. And then the hydrogenation reactor and the purification is all down here. You can see the real advantage. Most of the investment is in the oxidizer. If you take all that inert out of there, the downstream investment becomes significantly less. So a real advantage in operating in this mode. So the process is still running, has been now for nearly 5 years, I guess. There are many other opportunities for anaerobic oxidations. I mean, I could give you lots more examples here, but I think I've shown you enough that there really is an incentive. Nobody except us has commercialized one of these processes yet, but I think down the road this will happen at some point. Orthoxylene diphthalic anhydride is a great opportunity. Dehydrogenation of ethyl benzene to styrene, isobutylene to methyl product that we're interested down at the bottom here. The real advantage here is an oxidative dehydrogenation produces water as a byproduct and not carbon dioxide, generates energy, which could be used somewhere on the plant presumably, so we don't have to provide energy to that process. And then maybe we can even go directly to the oxidized product that we're interested in. So let me give you several examples now of the state-of-the-art in several of these paraffin oxidation processes. The one that has been looked at the most is propane and oxidation directly to acrylonitrile instead of going from propane to propylene and propylene to acrylonitrile. This has been studied most extensively by Ohio and now BP. Mitsubishi has a large number of patents in this area as well. And it's really remarkable the progress that has been made in this area since we first started hearing about it over 10 years ago, I think. Conversions are now up close to 80%, going directly from propane to acrylonitrile. Selectivity is still not where we'd like them to be, but in the mid-60s, which is pretty remarkable to go in one step from propane to acrylonitrile. So there have been some significant advances there. Propane is a lot cheaper than propylene. The economics look pretty good for this process. BP has announced that they are actually building or operating a pilot plant in this area, and the economics look attractive at specific locations in the world where propane is readily available. Acrylic acid has been a tougher one. Typically, the process goes like this. Propane is oxidized to propylene, or dehydrogenated to propylene. Propylene then goes to a mixture of acrolein and acrylic acid, or stops at acrolein, and then a second catalyst system is used to oxidize the acrolein to the acrylic acid. Shown here some key players in the area. Roman Haas has the best results that I have found recently in going directly from propane to acrylic acid, 71% conversion of propane at 60% selectivity to acrylic acid. Now, that's a really remarkable reaction. So my hat goes off to those folks, and I hope they commercialize that sometime down the road here. Isobutane is a tougher molecule to oxidize. We've actually spent some time ourselves looking at this. reaction. Isobutane today usually goes through isobutylene or tertiary butanol, which is then oxidized to methacrolium, and then in a second step to methacrylic acid. Sumitomo has most of the patents in this area that I've found. This is still, there's still a long ways to go here, but recently they've been able to get the conversion up to about 25% with this molybdate-based catalyst system, and a selectivity of around 45% to methacrolium and methacrylic acid. So still a ways to go, but in the last 3 or 4 years, great advance in conversion while keeping the selectivity reasonable. Well, Bob Griselli has a patent when he was at Mobil on an interesting way to do oxidative, to do dehydrogenations. And the idea there is to shift the equilibrium. So we're taking a hydrocarbon like propane to propylene plus hydrogen. It's an equilibrium limited reaction, requires energy to drive that reaction, and the conversion is limited at 550 to, let's see, 25% equilibrium conversion. What Bob suggested was to put in series here what he called a selective hydrogen combustion catalyst system. So he would run the first reaction using a platinum tin ZSM5 type catalyst, standard dehydrogenation catalyst, but then in the second reactor he would take this effluent, selectively oxidize the hydrogen. Don't touch the propylene, don't touch the propane, selectively oxidize the hydrogen. That then allows you to shift the equilibrium again because the hydrogen has gone now to make water, and in a second dehydrogenation reaction the higher conversion will take place to give you propane, propylene, and hydrogen. In this oxidation reaction here, he was using an indium catalyst supported on zirconia. The net effect was an increase from 25 to 30% in the conversion. So, you know, it's a small but a significant step forward. His next approach in the same patent was to combine both catalysts into a single reactor. So as you're doing the dehydrogenation, or the dehydrogenation, the oxidation catalyst will selectively oxidize only the hydrogen, not touch the propylene or the propane. So combined these two catalyst systems in a single reactor, and found that he could get 48% yield now to propylene versus the 20% equilibrium yield under the conditions he reported. So this was a very significant advance, not a significant decrease in selectivity, 95 to 90%, but much higher conversion in that process. The only problem is you're operating a catalyst that really wants to be reduced in an oxidizing environment. So the catalyst slowly gets oxidized, or the oxidation catalyst gets reduced, and he loses activity. So Bob comments that we still have some work to do there, but he's optimistic that they can find a system that ultimately might work in a single reactor system to go high yield to propylene from propane. All right, now let's move on to another area, and that is to kind of get out of the box that we're in here. Instead of trying to continually improve the catalyst, can we do something a little bit different and come up with totally new chemistry that's going to reduce CO2 emissions? And I've got actually 3 examples. I thought John Monnier might be here from Eastman, my good friend John, and as most of you know, they have for many years been looking at the oxidation of butadiene to the monoepoxide, which in a series of steps there, they cyclize it and hydrogenate it, actually end up with tetrahydrofuran. The only reason I put this in here is because it's the right sort of thinking, green chemistry thinking, to get us to 100% yield in these processes. This is a 100% economy reaction. It's the right chemistry to use. Unfortunately, butadiene is still more expensive than butane, so economics and not environmental issues are still driving new investment today. And it looks like Eastman is probably not going to commercialize this. They've been working on this for so many years. You probably heard talks at this symposium from John and others. It's wonderful chemistry, wonderful catalysis. He deserves an awful lot of credit. Significantly reduces the amount of CO2 that one uses in making tetrahydrofuran, but I guess the technology is now up for sale. Okay, let's go back now to the synthesis of methyl methacrylate. Goes into lucite and these Lexan shields and so on and so forth. Starting off with isobutylene, using a complicated metal oxide system. The oxygen oxidizes the isobutylene to methacrylene. Selectivity is not bad, high conversion to make methacrylene. Second step, traditionally or conventionally, is to oxidize the methacrylene to methacrylic acid. Complicated system again. Selectivity is not as high as it is up here. So the overall yield is around 75% to make methacrylic acid. Then you've got an acid catalyzed esterification. So you've got a three-step process, two high investment, high energy, relatively non-selective processes to make the methacrylic acid and then the dimerization. Well, Asahi Chemical came up with a twist on this that allows them to do this whole process in two steps. So they take isobutylene, oxidize it to methacrylene. They have a catalyst that they've patented, very high conversion, very high selectivity. Now the idea, they got a little bit out of the box there and said, okay, we really don't want to make methacrylic acid, we want to make the ester. So let's do an oxidative esterification. So they were totally able to eliminate that second high investment, high gas phase process, and they've dropped down to a liquid phase, low temperature, oxidative esterification to take the aldehyde to the ester with methanol and oxygen directly. Okay, big advance in this technology. So they do the conventional synthesis of methacrylene, do the oxidative esterification to methyl methacrylate. Two companies have been very active here. Asahi Chemical is reported to be building a commercial plant at 100+ million pounds per year that should start up, I think, next year sometime. Not sure about the date, but that's what I've heard. So the overall process, the second step now, goes in very, very high selectivity. Look at the Asahi Chemical results. 98% conversion of the methacrylene to methyl methacrylate at 96% selectivity. So the overall process has a much higher yield, over 90% overall yield compared to 75%, significant reduction in the amount of carbon dioxide that's generated in the process. They operate at 80 degrees centigrade instead of 350 degrees centigrade in that second step, and it looks like this is the way to go to make methyl methacrylate in the future. So fine job in that area. I'd be surprised if nobody had ever heard Lanny Schmidt talk about his ultra-short contact time catalysis, where he operates at 1,000, 900,000 degrees centigrade, passes methane and oxygen over a catalyst. The thing glows. It burns the oxygen in situ, and he's able to make oxidized species, olefins, by an oxidative dehydrogenation at very, very high temperatures. I wanted to put this data in here just to lead on to the second area, and that is the use of alternate conditions in addition to unusual conditions. Who would think that you can get higher selectivity at 1,000 degrees in a process like this? But he adds hydrogen now along with his oxygen. The hydrogen is used to combust the oxygen in the process to provide the heat to do the dehydrogenation of ethane to ethylene. So the hydrogen removes the oxygen, so it's not available for the high temperature, radical catalyzed, non-selective reactions. And he's able to get 85% selectivity to ethylene from ethane at nearly 1,000 degrees centigrade. So clearly a new out-of-the-box way to do things. So let's move on to these non-traditional oxidants. I think there's a real opportunity here as we move ahead. This work was really pioneered by Panoff at the Breskov Institute of Catalysis. He did a really superb job, and he found that iron-modified ZSM5 was very, very, very active and selective for converting N2O and benzene to phenol and nitrogen. Selectivity is extremely high, 99% in this process. They then formed a partnership with Monsanto, now Solutia, to commercialize this technology. And I'll show you the status of that process in just a minute. But the mechanism is very interesting. They're proposing there are these alpha sites on the catalyst surface. The N2O sits down on the surface of the catalyst, decomposes to give nitrogen, and this oxygen, alpha oxygen site on the surface that's very, very stable. This oxygen on the surface then reacts with benzene to give phenol that is desorbed to regenerate this vacant alpha site, which can react with more N2O. And what's very neat about this whole process, reported by AMIG, is that this alpha oxygen is very stable and very reactive. And in fact, he reports that you can take this alpha oxygen on the surface down to as low as, let's see here, I have this here somewhere. I think it's like minus 40 degrees centigrade, minus 40, and still react that alpha oxygen with methane to give methanol. So it's a very, very reactive, very stable site on the surface. So that's the mechanism proposed by Panov and the Solutia group. Their intention is to commercialize this in an improved process to make adipic acid. Now, we at DuPont and most other people in the world take benzene, hydrogenated cyclohexane, oxidize it to cyclohexanol, cyclohexanone. This mixture is then oxidized with nitric acid to give adipic acid. There's a very large amount of N2O that's produced in this oxidation with nitric acid. For many years, that N2O was vented to the atmosphere, was not considered to be particularly harmful, but it then became known that it was a ozone depleting gas and a global warming gas. So all of the nylon 6 and 6,6 producers got together and agreed to reduce N2O venting by one technique or the other. We decided to take the easy approach, which wasn't so easy, but just to decompose N2O back to nitrogen and oxygen. That's now commercial at all of our plants in the world, so we've taken care of that problem. Solutia decided, and this was the right decision, to use that nice source of activated oxygen. You've got N2O here, and why not use it to react with benzene using the Panov catalyst to make phenol, which you can then convert to cyclohexanone and nitric acid oxidize it. So by using this N2O, you can get incremental capacity in the plant to oxidize phenol, or to make phenol, and then convert that into adipic acid. There are several advantages in this process. One, the biggest advantage, is that you're avoiding the least selective part of this whole process, which is the radical reaction of making the ketone and alcohol from cyclohexane, because you're coming in here now, you're making cyclohexanone in very high selectivity. So as a way to expand adipic acid capacity by using that N2O, this is economically a wonderful incremental improvement in the process. So they actually built a pilot plant, and the results that I've been able to find so far look very, very encouraging. So the N2O is using this Panov chemistry, 400 degrees centigrade, 1 to 2 second contact time. Selectivity in their pilot plant, which they call alpha ox, which is rather appropriate, is very, very high at 98% selectivity. The productivity is 400 grams, 0.4 kilograms per catalyst. Per kilogram of catalyst per hour. Pretty decent productivity in that process. So all of these results are very encouraging. I don't think they have gone commercial with this yet, but they've certainly demonstrated that everything works out well in the pilot plant. Now, to use this technology anywhere else, one has to have a source of N2O, and that's been a big issue all these years. It's not been an easy or very cheap molecule to get your hands on. So Panov and the Solutia folks, I should say Solutia funded the work at the Breskov Institute. They actually have developed a very nice new catalyst, bismuth manganese catalyst supported on alumina, to make N2O by the oxidation of ammonia directly. Good job, Alex. Yeah. Works very, very well. Selectivity in this process, 92% to N2O from ammonia, at very, very high conversion. And they're claiming that the cost of N2O is about 25% of the cost of hydrogen peroxide. So if this is real, if it gets scaled up, I think we'll see a lot more oxidations taking place with N2O in the future. Just one slide here on the use of titanium silicalite. We saw this similar chart yesterday. Fantastic amount of work by the folks at Enichem. The first commercial application is likely to be in the production of caprolactam, but it just goes to show you the wide range of molecules that can be made by using titanium silicalite type catalyst and hydrogen peroxide. I mean, lots and lots of oxidized species there. Gets away from generation of carbon dioxide. Hydrogen peroxide and alkyl hydroperoxides are still too expensive to use. I'll have a comment on that shortly. But it shows you that there is, once again, emerging technology to reduce CO2 emissions by using new types of selective oxidations. Hydrogen-oxygen mixtures have been talked about for a long time. Extremely hazardous mixture to work with. Concentrate on this slide for the time being. We worked for nearly 20 years on combining hydrogen and oxygen directly to hydrogen peroxide. And the best catalyst system that we came up with was a 10% palladium platinum combination catalyst. And shown here as you vary the palladium and platinum ratio, the best results we were able to get were about nearly 70% selectivity directly to hydrogen peroxide from hydrogen oxygen. Now this is hazardous. We're using 2,000 pound pressure of oxygen and feeding in 95% 2,000 pound pressure oxygen, 5% hydrogen in an autoclave. If you don't do it right, I mean, you'll burn up metal very, very quickly. And we had a number of explosions. It's contained. We were protecting ourselves against that. And you could burn through 2 inches of metal instantly using a metal catalyst. Sometimes if it gets wet and gets dry, it can ignite all that oxygen in there, and the fuel then becomes the metal reactor. And it's very exciting. But we actually ran this through a pilot plant. We learned how to control it. Modern day process control allows you to run this reaction, I think, safely, provided you could do it. Unfortunately, it was the cost of oxygen, the high pressure oxygen, that killed us. We could never get this reaction to go using low pressure air or oxygen and getting the kind of concentrations we wanted. We were able to make as much as 50% hydrogen peroxide solutions using hydrogen oxygen directly. Tremendous technology. Well, Wolfgang Hollerich, talked to Wolfgang many times about this catalyst system. He decided to go ahead and take the platinum palladium catalyst. Critical component is a sodium bromide promoter that's present in this system. So he took a titanium silicalite, vanadium silicalite type catalyst, the type of catalyst that does hydrogen peroxide epoxidations, deposited on that catalyst surface then the appropriate palladium and platinum catalyst, and used sodium bromide promoter. And these are the results he got for directly converting propylene with hydrogen and oxygen to propylene epoxide. 19% conversion and 87% selectivity to propylene oxide. This is a really remarkable reaction. And without the sodium bromide promoter, only 34% selectivity to propylene oxide. So this is an example, I think, of where we're headed in this area, using possibly hydrogen-oxygen mixtures instead of hydrogen peroxide. Safety will be an issue that everybody's going to have to learn to deal with. Let's move over to the last couple of examples here now to the use of carbon dioxide as an oxidant. This is work that has been studied to a great extent in China at the Dalian Institute, using chrome catalysts on various supports with carbon dioxide. It's possible to do an oxidative dehydrogenation of ethane with carbon dioxide and generate ethylene with pretty decent selectivities, up over 90% selectivity to ethylene at pretty decent conversions. In the case of chromium-3 on silica, which is the best catalyst, around 38% conversion of the propane with 95% selectivity to propylene. Now, you say to yourself, there's something wrong with this. This is thermodynamically not right. That's your first instinct. Well, I've shown here some additional results. They have spent a lot of time looking at promoted catalysts. They actually claim to have gone commercial in using this technology, carbon dioxide and ethyl benzene, in a refinery to do a dehydrogenation of the ethyl benzene to styrene with CO2. So they claim it's gone commercial. But you think about the thermodynamics, and it's a very complicated reaction which they have published. And they claim it takes place in two stages. There's this conventional dehydrogenation of ethane to ethylene, And then there's the reverse water gas shift reaction here, the hydrogen reacting with the CO2 that's present to generate CO and water. So that's how the hydrogen is removed from the reaction to shift the equilibrium. So, there still is an overall question I think a lot of people have on the thermodynamics of this process. Very clearly is dependent on the support. Silica appears to be the best support, but it looks like another opportunity to use up CO2, reduce the amount of CO2 that's made in some of these reactions, and come up with a nice way to make ethylene or other olefins. Another area that is developing, which is truly remarkable, catalysis, and that's to use nanoparticle size of gold as a catalyst. This is work pioneered by Haruta. He uses gold deposited on titania, on silica titania, and other materials. Dow, Bayer, a lot of people working in this area now. There's still some real problems from a conversion standpoint, but using gold, the old coinage metal, inert metal, turns out to be a very nice active catalyst for the selective oxidation of propylene to propylene oxide. Selectivities of 95, 99%. Unfortunately, the conversions are still fairly low. 1 or 2%, as high as maybe 4 or 5% in the literature. You'll find some examples. So, I don't know whether this is going anywhere or not, but it's another example of finding different catalysts to get high selectivity and reduce CO2 emissions. Well, the economics have to be right if we ever see any of this commercialized. And the problem is oxygen is still very cheap. It's essentially free. Bring it in out of the air. There is a little cost associated with dealing with it, but it's only a few cents a pound. And you have to deal with that issue in industry. N2O, this goes back to a Chemtech article in '98. They reported N2O costs at 17 cents a pound, hydrogen peroxide at around 50 cents a pound. If the new Panoff N2O technology is right, that may get us down to 10 cents, 15, 20 cents a pound for N2O, but it's still 10x the cost of oxygen. Hydrogen-oxygen mixtures have a real chance. Hydrogen is cheap. Very few moles of hydrogen are required in a process. So I think the future economically is with hydrogen-oxygen mixtures if you can deal with the safety aspects of that process. But these other non-traditional oxidants, I think, will come on board as taxes on CO2 become important at some point down the road. Or environmental issues become more important than they are today. Our current administration doesn't seem to be worried about global warming anymore. So these are the issues that are going to set things back a little bit. But someday down the road, over the next 100 years, some of these other oxidants are going to make it. It's time to do the catalysis now to get us ready for those future opportunities. So let's just finish up here with a few comments. I think I've given you enough examples to convince you that anaerobic oxidations, doing oxidations in the absence of gas phase oxygen, is the way to go. The selectivities can be higher. The non-selective formation and combustion to CO2 can be significantly reduced. Huge engineering issues. Took us a long time to start up that plant and get it running in Asturias, Spain, to do the transport bed reactor in an oxidative environment. But it's possible. And there is a real future there. These other oxidants, their time will come. Maybe not in the next few years, but at some point their time will come, and we need to get the catalyst technology ready to go for that time. Today, however, there are a lot of opportunities for using titanium silicalites and alkyl hydroperoxides, and especially chemical applications. That's happening today, and I think we'll see more and more of that in these very complicated pharmaceutical and agrochemical chemicals that are happening. So selectively, we're seeing it in use today, a large scale, and maybe not for a little while. Hydrogen-oxygen mixtures have tremendous potential, but as I've said several times, safety is an issue that's going to have to be dealt with. New technology is something we should all be thinking about. I think that was the basis for that item in the report coming out of those two workshops. We've got to continue to support new ideas, develop new technologies that do result in higher yields and lower investments for these processes to be commercialized. And finally, you've got your soapbox. Catalysis is still important to this country. It's still important to the world. It's not supported as much as it used to be. We're in a bit of a slump right now, but it's only with a lot of us getting up and telling the world that, hey, there still are good things to do out there and getting results. So I encourage all of you, where you can, to continue to promote new ideas, talk about new opportunities in catalysis, and get out of the box, do some new things. I'm really getting tired of seeing the same old reactions reported over and over again in Journal of Catalysis and so on. You know, you get kind of tired of every group studying the same copper ZSM5 catalyst for N2O and so on and so forth. You know, go look at something new. There are lots of new things to do out there. So that's the end of my talk today. Once again, I want to thank you for the opportunity to come down and talk to you, and I'll be happy to answer any questions you might have. Thank you.
Is there any work going on the capture of
CO2?
You know, like a tail gas reactor of some sort?
Yeah, you know, I don't know that technology well, but I understand there are some enzymes that will very, very nicely capture CO2, even at high temperatures, very effectively out of power plants and things of that sort. So there's a lot of talk, a lot of proposals for funding, and I think we'll see some things happening there, but I can't say specifically what's going on. Seems like an impossible thing, doesn't it? But hey, stranger things have happened.
We used to think that about reforming.
That's true. Yeah, that's right. That's right. You never say no.
Never say
In case of anaerobic oxidation, you depend definitely on this fluidized bed, the riser, and the complexity of and the cost, I guess, of that kind of an operation. Is there any work on membrane type oxygen transport membrane at high temperatures for that purpose?
Yeah, lots of ideas there. There are a number of research groups in the world doing exactly that, running a membrane reactor, feeding in, coating the inside of the membrane reactor with a VPO catalyst, providing the oxygen through the membrane to the surface of the VPO catalyst, doing the oxidation in an anaerobic type environment. That's another way to do it. That's right. There are several groups working in this area. I'm familiar with a couple of EC-funded projects that are actively being worked on. That may come. The only problem in that area is you've got to make darn sure you don't have a crack in your reactor and the oxygen doesn't get into that high hydrocarbon rich stream. Otherwise, you've got a real problem in your hands. But it is an area that is being actively looked at.
But if that's safety problem or against materials problem
Yep.
or so, is the economics right for that?
I think the economics are right for that. Yep, sure.
So the transport rate of oxygen is enough to
Yes.
high volume.
Yes, the potential is there, and the advantage, of course, is you don't have a moving bed. So you just pack your reactor and just feed in the oxygen along the reactor. Yeah, it's a great opportunity.
Just an off-the-wall question. You talked about CO2 and the problem of sequestering it from the atmosphere. I know that in our process it's probably very similar. When you make CO2, you trap it with an alkaline solution. Are you aware of any catalysis it takes, for us, it's a carbonate, and converts that carbonate into useful chemical products?
There are ways to do that. Unfortunately, it usually requires a lot of energy to do it. You're working your way back uphill again.
Right.
But if we get into solar-based economy or nuclear energy and electricity becomes cheap and you don't generate CO2, who knows? Maybe you can use these other processes. But there's not a lot of work that I'm aware of that's going on. Take carbonates. Any more questions? Let's thank our keynote speaker again.